So this is the second video, and we are going to look at the problems. Now, looking at the problems, yani if you just want to recall what we have taken before, right? I think it's a good idea to look at, say, what we have taken in chapter 2 and chapter 4 and 5. Looking at chapter 2, under this case, this is the one here. So looking at chapter 2, a free call. I'll go to the problems directly just to give you an idea. So this was the signal conditioning. It could be anything to anything, and somehow, mainly voltage to current or current to voltage or resistance maybe as well. Change to voltage change as we have in the bridges, for example, or it could be pressure to current or current to pressure. We want to see those examples in which we have a linear relationship, for example, for this signal conditioning. And so that was kind of a problem in which we have linear relationships. And we also studied how to have a linear relationship in which instead of plotting y against x, we can plot y against 1 over x. Okay, or y against x squared. And in this case, we can get a straight line equation. So these are kind of another problems that we can have as well. Other kind of problems that is related to the divider circuit. So the divider circuit, or if we have a load RL, we need to consider the Thevenin's theorem so that we can include the load. So just to look at, so this was an example in which we had a transfer function, and again, because of this load, because of the load that I have, where's the load here? So we have a load. If you can remember, amplifier outputs a voltage that is 10 times the voltage on its input terminals. It has an input resistance of 10 kilo ohms and sensor output of voltage proportion to temperature with the transfer function of 20. So we have a transfer function in which the input is degree centigrade and the output is millivolts. So the input is temperature, the output is in millivolts, in voltage. So in this case, if I have 10 degrees, so the output voltage will be 200. The sensor has an output resistance of 5 kilo ohms. If the temperature is 50, now 50, you can say, well, if it's 50 degrees, you can say, well, it's 50 times 20, which is 1000 millivolts, which is, is it 1000? Yes, 1000 millivolts. In this case, you're going to calculate it and say 20 times 50 is 1 volts. And because it has 10 as a gain, which is the gain here, is going to be multiplied by 10, so you're going to have 10 volts. But because we have a load, things are going to be different, and we need to consider the Thevenin part, in which I'm adding the R load, okay, the R load. And adding the R load will give me a different voltage in. So in this case, instead of having a voltage of I, which I assume is 1, now it becomes 0.67 because of that load, because it is actually divided because of that load. And that's why we have 6.7 volts. Now, in this case, we started giving the idea about the divider circuit, in which we see that if you want to calculate VD, in this case, which is on R2, so this is R2 divided by the sum of the R's, R1 over R2, times the supply voltage. If I want the voltage on R1, so it's R1 divided by the sum of the R's into voltage supply. So this is another kind of questions that we can get for the divider voltage. I'm not going to go to the problems in the PowerPoint. The bridge circuit is other type of questions that you may get also in the exam, and recall that this is what we have as an equation. In this case, one of those resistors is going to be the R4, for example, in this case. Okay, so this is how if I say that R2 into R4 is equal to R1 times R3, and in this case, if R1 into R3, so if R2 into R3, now this is the equation. It's what I said is correct, but this is applied to a different shape than the one that I have, because this is referring to a different figure. Okay, so again, if R2 into RTD is equal to R3 into R1, in this case, R3 into R2 is equal to R1 to R4. So these cancel each other, and so we have a null voltage which is 0. Now the null voltage is going to change because the RTD resistance is changing, and this is why we have a different answer. And these are the problems we solved in this case. And then we said that the galvanometer, when you use a galvanometer, there's a resistance in that detector. The galvanometer detector has a resistance in it, and because it has a resistance in it, we need to consider that using the Thevenin resistance. And this is how we calculate the Thevenin resistance, and based on that we also, if someone is asking about the current, we can calculate the current, but mainly the Thevenin resistance is very important to calculate, and that is reflected very clearly in our delta V. So this is another type of a question that you may have if we are using a galvanometer which has an internal resistance. That means we need to use the Thevenin theorem. And in this case, you can see that the Thevenin is minus 30.9, and then of course you put the Thevenin theorem to calculate how much the current you have in this problem. And again, there was another problem that is also very similarly to the Thevenin's theorem, to the Wheatstone bridge. And then you have the RC filters. You have the low pass filter, the high pass filter. Make sure you know how is the design of those filters. So the low pass and high pass, and this is the equation of the cutoff frequency, and then you're going to calculate how much attenuation you have, and that was just an example of that. Make sure that you go through this example for the low pass filter and the high pass filter, in which it's exactly the same equation, except in the numerator you have F over FC, and again we also solved the band pass filter. It has both the low pass and the high pass filter in this case. So that's all for this part, and then we solved many problems. I'm not going to solve the problems again here, okay, but I'm just trying to cover up the third part. So I talked about the divider circuit, the Wheatstone bridge, and the pass filters, and now we're talking about the operation amplifier circuits. So the operation amplifier circuits, so we have an operation amplifier. Let us go to the equations directly. So this is just a comparator of two different voltages, in which the output is just the difference between the voltage times the amplification. Or you can have a unity, of course, if you want the output to be unity, and sometimes you just unity just to change the sign of the voltage. In this case, this is an inverting that goes to the minus sign. The Vn goes to the minus sign. So you have the ratio of R2 over R1, which identifies the amplification, the A0 in this case. So the A0 here is R minus RF over Rn. And that was an example. The non-inverting, in which you have the Vn in the plus sign, and the equation out will be different. In this case, our amplification is 1 plus R2 over R1. And of course, there are summing amplifiers which has different equation. So this is one of the equations. There's also the current to voltage converter. In this case, I think so. That was I only taught you till summing amplifiers. These are not required. These are not required to study. So this is the problems that you may get. Now, someone may ask me, what else do we have as problems? Well, there are other problems. And again, if I go back to the problems, so we can have problems that has like the idea of the transfer functions. So this is simple, but you still need it. You need to remember the terms of resolution, accuracy, error, hysteresis, linearity, non-linearity, precision, accuracy, sensitivity. So these are just terminologies, and stability in this case. At least you understand the reliability with dependability. Now we have a problem here where we can calculate what is the reliability of the system and what is the probability of failure, which depends on the failure rate, which is mu. So if you go and look at the failure rate, for example, this is a failure rate. So you have a control valve, and the failure rate is 0.6. So the mu is 0.6. So if you go back, you substitute 0.6, and if you're calculating the rate for 1 year, so you're going to substitute T for 1 year, and you will have what is the reliability for 1 year. And if you go back just to look at why did I say T is equal to 1 year, because here the fault is per year. Okay, so if it was per month, then I need to substitute T for months. So this is a kind of a question. What else of questions do we have? Well, now you would expect, of course, other than the questions or problems, I would ask you to explain a sensor where you're going to identify the input, the output, the operation, and the applications. And of course, these equations are going to be given to you in the equation sheet, and we are going to solve some problems just to make sure that you know them. Here again, the strain gauge pressure sensor, which is another, those sensors that you need. And remember that this one also has another equation, which is R into GF into L into over delta L. Diaphragm pressure sensors, it has another equation, which is here, delta V is equal to P times A divided by K. You don't need to memorize the equations again, right? Just you need to understand them so that you know how to apply them. Again, the capacitive depends on the dielectric constants with the ER and the permittivity of the pre-space, which is E naught or epsilon naught. A is the area of the plates, and D is the separation between the plates, the distance between them, and so on. So you have flow sensors, a group of flow sensors, and you have an ultrasonic sensor, the level sensor. Again, I will ask you to explain this, where I want you to identify what is the input, what is the output, what is the operation, which means how does it work, and give me an example of an application where you're going to say it is used as an application. For example, for the float sensor, it's used in the water tanks at home or in some kind of fuel level monitoring in some places. These are more and more sensors. As you remember, pressure sensors, it has equations. This is the thermocouple, where there's an equation for the Seebeck effect, which is given to you usually. And if you have the difference in temperatures, you just take the difference and multiply by the Seebeck coefficient to find the voltage. Here we took the interpolation, where we calculate the interpolation if you have the voltage, how to calculate the temperature. And this is an RTD, in which the RTD has the equation, which is R is equal to R naught into 1 plus alpha, which is the temperature coefficient, to delta T. So alpha is given to you, the delta T is given to you, the initial resistance given to you, so you're going to find the final resistance. Okay, so then we have taken the idea of the self-heating, which is similar to loading, but it's something different. Yeah, this is related to self-heating, and we have taken examples of self-heating. Please make sure that you understand these examples of the self-heating. So I'm not going through it again. Thermistors, it has an equation which is exponential. Okay, and you also have the divider circuit. This is simple. This is just how much does it bend, which depends on the equation, which is L is equal to L naught into 1 plus gamma delta T, which is very similar like the resistance for the RTD, exactly the same concept as well. And this is just an example here for the calculation. This is exactly the same concept, where the volume is equal to volume to 1 plus beta delta T, very exactly the same equation that we have. Now, gas thermometers, it depends on the PV of the ideal gas law. PV is equal to nRT. If you have a thermometer, the number of moles does not change if the temperature changes. If it is in an enclosed, in a closed tube, and in this case, because a closed tube, you're going to cancel the volume. You have N1 is equal to N2, and you're going to cancel the volumes and the universal gas constant. So you're going to be left with P1 over T1 is equal to P2 over T2. So this is simple, but you need to know how to solve. This is another problem that we said that how you're going to calculate the resistance based on the metal resistance based on the temperature. Mainly, again, this equation is very important, and this equation is actually a linear equation, and alpha naught is just a reflection of that equation, rearranging it. And then we said that, well, we can have a better approximation if we have it to the power 2, which is a quadratic approximation. And we have taken an example of if you have a data of t and r, so you're going to have approximation of t and r as a linear relationship, or then you're going to have it as an two equations, two unknowns to solve for alpha 1 and alpha 2. So these were the answers. Okay, so these are the problems. Now, going through all these problems that we already have went, so we want to see what kind of a problem that I could have. I already gave you all these problems are possible to be appearing there. Let's see what do we have here in the summary that I have collected. So you have a voltage divider. A sensor produces a voltage of 0.2 to 0.6 volts. Design a signal conditioning circuit to convert this into 0 to 5 volts. So we have a signal conditioning changing 0.2 to 0.6 to 0 to 5. Assume an amplifier gain is used after bias adjustment. Okay, so what do we have? You're saying that 0.2 represents like 0 and 0.6 like represents this 5. It's like you're having x2 and x1 and y1 and x2 and y2, and here you're trying to just to rearrange that so that you can find out what is the linear relationship between these two. Now, in this case, here he tried to solve it, just saying that subtract 0.2 to make this 0.2 0. In this case, I'm having like the sensor changing from 0 to 0.4, and then I'm taking the slope. In this case, the slope will not change, which is delta y over delta x, which will be 12.5. Now, this somehow looks like it's confusing, but if you will use the x1, x2, y1, and y2 linear relationship, you're going to get the same answer. And actually here, I can see that they did not get the same answer as we have expected. We got the same answer, but we did not get the equation. He did not give us the equation. Going to the filter design a low pass filter. Now that is a good question, in which I have a FC is equal to 1 over 2 pi RC. Remember that you can always select the value of R or C. Now the way that we have solved, we selected the value of C, if you can recall. So let's go to look at one of the pass filters. So now here, this is a pass filter, a low pass filter to attenuate. Now again, attenuate is the opposite like of whatever you're trying to save. So attenuate is you're attenuating 0.5 megahertz by 97%, means that there's only 3% left. Now based on that, which is V out over Vn, which is the 3% left, is equal to 1 over 1 plus this is the equation of the low pass filter. Now what is the frequency? Let's read it again. A low pass needs to attenuate 0.0 megahertz, so you need to substitute the frequency. Thus, we find the critical frequency. We find out the critical frequency that will attenuate 97%. So that means V out over Vn. Okay, V out over Vn is 3%, which means the voltage output is only 3% of the voltage input. And in case that we are substituting here the high frequency. This is exactly what you want. And then we find out what is FC. Now FC is equal to 1 over 2 pi RC, and as we said, if we assume that C is, for example, is 0.01 microfarad, which is a good assumption, then the resistance is going to be 1.06 kilo ohms in this case. And so this is the first part of the problem. Now if someone asks me another question, now if I have a 400 hertz, which is a low frequency, so when I substitute 400 hertz, I would expect this 400 hertz would pass totally, because this is a low pass filter. It passes 400, but it will not pass 0.5 megahertz. So when I substitute 400, we find the answer is like 99.96%, which is really good. So these are the type of questions that you would expect and the problems for the pass filters. Now going to the sensor transducers, like this is just a simple question. An RT has a resistance of 100 ohms at 0 degrees and a temperature coefficient alpha of 0.00385. Find the resistance at 50 degrees centigrade. In this case, what do I have? I have a resistance R naught, I have T naught, and I have the final T. Delta T, if I will look at delta T, is 50 minus 0. Okay, so the answer is here, RT is equal to R naught. R naught is 100 ohms. 1 plus alpha, alpha is given, and delta T is simply 50 minus 0. So that is 50, and you will have the answer of the new resistance, which means the resistance changed from 100 to 119. The resistance increased when we increase the temperature. Okay, so this is like an answer. Another question that could be for the piezoelectric sensor, in which we have an equation. Now let me put it in a better way. I mean, this is confusing. Sorry. So just let me verify the equation. So we have the equation for the piezoelectric sensor. So let's see, where is the piezoelectric sensor? Okay, so the piezoelectric, we use that for pressure. So let me go to the pressure part. Okay, so that is pressure. And here's the piezoelectric sensor. So V is equal to D times sigma. And in this case, V is equal to D times sigma. Yeah, so that is the equation. V is equal to D times sigma. So a piezoelectric coefficient has a coefficient of D is equal to 100. And this is just a unit. So it's 100. Calculate the output voltage when the pressure of 50 kilopascal. So we have here a pressure, which is 50 kilopascals applied to an area of 0.01 meter square. Now, if we have pressure and we have area, we can find the force. Okay, so in this case, we can find the force, and then we can have the equation. Now, V is equal to D times sigma. Now, let's see, what is D times sigma? What is sigma? Sigma is the mechanical stress. Okay, so we already have the mechanical stress, and D is the piezoelectric coefficient. Good. So what do we have here? We have the coefficient, which is 100, and we have the stress. The stress is actually force divided by area, which is the pressure. And in this case, I think so we already have the pressure. And if I would guess that there was a force, then it would have been a better question that this is force and this is Newton, for example. And here I'm going to have this force, and I have the area. So I have force divided by area, which is pressure, which is the stress. In this case, now this is a better, which is sigma, which is equal to the pressure in this case. And then we just multiply by the coefficient, which is given to us, 100. Okay. I understand that there will be unit conversions, so be aware of it. Okay, so just simple problems, just to see that you have an idea about these simple problems that we are taking. We will have more problems, but I will finish my second video, and then I will going to start my third video in a moment.